Today, we want to continue looking at graphs of sinusoidal functions and how we can build sinusoidal functions. The four things that we're looking for: the middle, the vertical shift, the amplitude, the period, and the horizontal shift. Those four things we put together to build a sinusoidal function. Yesterday modulo this class, on Tuesday, we found that there are many functions that will give us the same graph. We have a choice of where we can think of our functions starting at the top, the bottom, the middle going up, or the middle going down, which would cause us to use positive cosine, negative cosine, positive sine, or negative sine. So really, there's kind of five things that we're deciding. So let's take a look at an application of this idea. So on June 21st, there were 15.35 hours of daylight. And on December 21st, there were 9.02 hours of daylight in Grand Rapids. I found this problem, and this problem is specifically referring to the daylight hours in Grand Rapids. I think the dude that wrote the problem lives in Grand Rapids, and I'm like, oh, well, I'm going to take that part of the problem too. So the additional information that we'll have is that on June 21st, this is when we have the most daylight. So this is going to be the summer solstice. That's going to be the most daylight. And then on December 21st, that's going to be our winter solstice. And so that will be our least daylight. That's the significance of the two pieces of information that you've been given. So there's our winter. And so that's going to be our least daylight. So we can see the sinusoidal function showing up already. I've got a point for the top, and I've got a point for the bottom. So I'm going to start my graph on top, and it's going to drop down to the middle, and then it's going to hit the bottom, and it's going to go back up to the middle, and then back up to the top. And we're going to try to find all the pieces of information that we need to build a function using this information. So here, it looks like the top is going to be 15.35 hours of daylight. So this is going to happen at 15.35. And at the bottom, we'll have 9.02 hours. So we've got twice the amplitude. We need to figure out where the middle is. And that'll just be halfway between the top and the bottom. So let's make that calculation. I'm just going to take the average of the 1535 and the 9.02. So 15.35 and the 9.02 divided by 2. So the middle is going to be at 12.185. I'll go 12.19 to match the same decimal places as the others. So the first thing that we're going to do is calculate the middle. And I just did that with the average of the top and the bottom. So the middle will be the average of the top and the bottom. Oops. We need to know the amplitude, and that's the distance from the top to the middle. So I'll take the 15.35 and I'll subtract the 12.19, and that'll be our amplitude. So I'll take the 15.35 and subtract my 12.19. And I get 3.17. Now we've got all of our vertical information sorted out. We can also take the middle minus the bottom to come up with the 3.17 as well. So the 12.19 minus the 9.02 will also give us an amplitude of 3.17. So we've got the middle, we've got the amplitude, halfway to making a function out of all of this, or maybe 40% if we're saying there's 5 pieces of information. Now, we know that the most daylight is happening here on the summer solstice, and that's June 21st, and then the winter solstice is on December 21st. So if we look at what we were looking for, we want the function f of t for the amount of daylight on day t of the year. So I need to translate June 21st and December 21st to the teeth day of the year. So fortunately for us, the internet is available. I found this. So June 21st looks like, on a non-leap year, looks like day 172. So it looks like June 21st is day 172. So on 172, we had 15.35 hours of daylight. And December 21st, when we had the least daylight, is day 355. So the number of days from the highest high point to the low point is 355 minus 172, and that's going to be 1/2 of a period. So 1/2 the period is just going to be the difference between 355 and 172. So 183. So if we double this, that will give us 1 whole period. We should expect this to be about a year. So we should expect we're going to get 366. So 1 period is 2 times 183. $366. It's a little bit off. This has to do with the fact that it's not an exact number of days that it takes the Earth to go around the sun. 1 year is not a very specific, rounded off to the nearest one exact number of days. It's a little bit more than a day. There's like an extra quarter day. So we have a period of 366. This is not the number that's going to go into our function. The number that's going to go into our function is, we call b, and b is 2 pi divided by the period. So 2 pi divided by the 366. And now we're like, oh dang, half the period is 183, and that's the number that I want to drop down here anyway. So b is going to be pi over 183. That's going to stretch our period out to 366 days. Now we just got to pick a starting place to get our horizontal shift and the trig function that we're going to use. So let's start off at, let's take 172 as our horizontal shift, and we'll write the function in terms of positive cosine. So our equation f of t, or our function f of t, I'll put the middle, 12.19. We're doing positive cosine, so plus 3.17, the amplitude, times the cosine of, the coefficient of t will be pi over 183. And my horizontal shift is 172. Now we have a formula for calculating the number of hours of daylight on day t of the year. Any questions?
Oh, where did you get the 172 and the 355?
The 172 is, I chose the top, this first point, as my starting point. So since it's at the top, I chose plus cosine, and the horizontal is 172. 172 is the day of the year. That's June 21st. That one I had to look up.
Oh, thank you, thank you.
If we would just start counting days of the year, we wouldn't have to worry about these formats of like 21 June or June 21. It would just be 172. I don't think that would really work very well. I heard that, I think it was in France, they wanted to come up with a separate day for every single day of the, a separate name for every day of the year. And I thought that was a plan that was not only terrifying, but awesome at the same time. So what are we going to do with a function like this? With this function, we can do the same thing in math class anyway, that we always do with functions. I can give you a value of t and ask you to find the number, a day of the year, and ask you to find the number of hours. I can also say, here's a number of hours. What days would you predict have those hours of daylight? So given a function, we can play input-output game, the input-output game. I can ask you to find a given t, find f of t. Given an input, find the output by plugging things in. Or I can give you an output and ask you to find the input. I can ask you to solve f of t is equal to some constant. I'll use k, the mortal constant. So for example, let's write down our function again. So f of t was 12.19 plus 3.17 times the cosine of pi over 183 times t minus 172. This gives the number of hours of daylight in Grand Rapids on the Tth day of the year. So I could ask a question. How many hours of daylight on July 12, which is day 190 something, 193. So I've given you a value of t and asked for the hours of daylight. We just need to take the 193 and plug it into the function. So f of 193 is 12.19 plus 3.17 times the cosine of pi over 183 times t minus 193. Oops, t is 193. Times 193 minus 172. I switch this down to single line syntax. So because the next thing I'm going to be doing is asking a calculator for this calculation. So I got 12.19 plus 3.17 times the cosine of my coefficient pi divided by 183 times 193 minus 172. So 193 minus 172, that'll be how many days have passed since June 21st. So it looks like on July 12th, there will be 15.16 hours of daylight. Any questions? So we could ask the question in the other direction. On what day will there be, then fill in the blank, the number of hours of daylight? So let's say on what day will there be, this is all in Grand Rapids. On what day will there be 12 hours of day or 13 hours of daylight? I want 12. I had to pick a number and I got stumped on picking a number. On what day or days will there be 12 hours of daylight? So at this point, we're going to need to solve an equation. Also, I threw in that S in parentheses after days because we should expect there to be more than one day where there's going to be 12 hours of daylight. Because we go up to the 15.13 and drop all the way down to 9.02. So we're going to hit 12 hours on the way up to 15 and then 12 hours on the way back down to 9.02. So let's figure out on what days will there be 12 hours of daylight. At this point, we need to solve an equation. So we're solving the equation. (12.19 plus 3.17 times the cosine of pi over 183 times t minus 172 equals 12. In the previous problem, you were given a number of days. Now I know why I wanted 13, because I used a 12 in the previous problem, and I try to keep things different. So on what days will there be 13 hours of daylight? So I want to solve the equation of 12.19 plus 317 cosine of pi over 183 times t minus 172 equals 13. A convenient way to solve an equation, especially since we know there's going to be more than one solution. A really convenient way to solve this will be to use a machine, specifically a graphing calculator, specifically our good graphing calculator. So I'm going to put the function on one line, 12.19 plus 3.17 times the cosine of pi over 183 times x minus 172, close inside, close those. And now I don't see a graph, so I'm gonna have to zoom out kind of a lot. So when we look at our graph and we just zoom out like I just did, we see that we have a bit of a scale problem. If we're just zooming out with the default scales on Desmos, notice that it doesn't look like it's changing much at all, because over a year, we're going from 0 to 365, but the number, so that scale is pretty large. But on my vertical scale, I'm between 9 and 15. So it doesn't make sense to just zoom out. So what we can do is go into the wrench and adjust our y-axis. Our x-axis needs to cover at least 1 year. So negative 58 to 615, maybe that's a little bit too much. Let's look at negative 31 up to 450. But the y-axis is too smushed. We can't see the graph going up and down. I know the lowest value is 9 and the highest value is 15. I want a little space above that. So what if I go up to 20 and put the bottom at, say, 7? Oops, not 716, 7. And we're in radians. Now we can see the graph going up and down. So now we can see this up and down motion. Here's our maximum of 15.36, which is not exactly what we had, but we made adjustments. 15.36 hours at 172 and 9.02 hours at, what is 35? 15.36 at 172 and 9.02 at 355. Now what we're looking for is when this graph is equal to 13. So if I graph the line y equals 13, I can find out the two places where this graph has a value of 13 in that first year between 0 and 365. So it looks like we have two solutions. T is equal to 95.5. I'll just round these off because they're days of the days, and 248. So it looks like on day 96 and on day 248, we'll have 13 hours of daylight. Let's see. I got to look them up. I can't do this math in my head. So day 96 is April 6th. And day 248 is September 5th. So on April 6th and September 5th, it looks like we'll have 13 hours of daylight. I had to look it up because I can't do those calculations. Any questions? All right, so this is just a variation on the classic input-output game. When you have a function, I can give you an input and ask you to find an output. I can give you an output and ask you to find an input. One thing that we kind of recognize about the particular function that we're dealing with, we know that over a year, we're going to have at least two answers, one on the way up and one on the way down. So on April 6th, we have 13 hours of daylight and it's increasing. And then on September 5th, we have 13 hours of daylight and it's decreasing. So we found these by using a graph. So this problem was no match for our calculator style. And this raises the question, though, what if we didn't want to use a calculator? At which point I'd be like, oh, dude, you're going to have to invert a cosine, and there's like a pi over 183. You're going to want to bring a calculator to this fight. So it does raise the question, what if we can't go through the whole graphing business? What if we just had to solve this by doing inverse operations in reverse order, by doing the same thing to both sides of the equation? Because we know that when we're solving equations, one of our strategies is just to do the same operation on both sides. That is, perform inverse operations in reverse order. So we should also be able to use inverse operations in reverse order. We should also be proficient in using inverse operations in reverse order to solve an equation. As messy as this equation sort of looks, the operations are mostly addition and subtraction, and multiplication. Sometimes we're multiplying by weird stuff like pi over 183. I don't know why I have decimals combined with my pi over 183, but we do strange things. But we also have this cosine. And we know that the cosine function is where we're going to end up with our two solutions. So let's take a look at what's going on in this equation. How does t become 13 in this equation? Let's read the equation. If we start with a value of t, the first thing that happens to the t is we subtract 172. So I'm just going to make a shorthand note of what's going on in this equation. After we subtract 172, then we multiply by pi over 183. No, border. People are making noise out there and they woke you up. Good boy. After we multiply that result by pi over 183, then we find the cosine of that result. So the third step is we do a cosine. After we find the cosine, then we'll multiply by 3.17. And then finally, we'll add 12.19. When we plugged in the 193, we had a calculator that could do all these operations at one time. If we happened to be using an iPhone calculator that had to do one step at a time, then this is the order of things that we would do. I would start with the 193 and subtract 172, 21. 21 days after June 21st. Then I'll multiply by pi over 183. So times pi divided by 183 is the 0.3605. Then we find the cosine of this answer. So cosine of this is the 0.935. Then we multiply this by the 3.17 to get the 2.97, and then we add our 12.19. And that gives us the 15.16 that we had before. So we're just writing down the order of operations. This is how t became the 15.16 in the previous problem. What we're trying to do now is the opposite of this. If we do these steps, we got to figure out where we started with t and ended up with 13 down here. So this is t turning into a 13. We've got to go the other direction and figure out how to turn 13 back into a t. So we're going to perform the inverse operations in reverse order. We need to figure out how to turn 13 back into a t. So we need to come up with a plan, and that plan should be inverse operations in reverse order. Whatever we started with t, the last thing that happened is we hit plus 12.19. So the first thing that we need to undo is plus 12.19. So our first step in undoing what this function did is to subtract 12.19. So I'll take the 13 and subtract 12.19. Hey, bud. Come here. We'll get a toy. 1 sec, please. There's a delivery on the street, and so we have to watch out. So the first thing that we're going to do is undo the last thing that happened. So the last thing that happened in the function going forward is to add 12.19. So the first thing we do is undo that 12.19. 13 minus 12.19 is 0.81. The second to last thing that happened was we multiplied by 3.17. So now we're going to undo this by dividing by 3.17. So I'll just take my result, the 0.81, and divide by 3.17. 0.2555205047. Now I'm going to undo the cosine. Right before we multiply by 3.17, we did the cosine. So here is where we're going to have to do a cosine inverse. And here is where our two solutions are going to show up. So if we just ask the calculator what the cosine inverse of this answer is, it's going to give us 1.31. Oops, we're not writing them down. But here is where our two answers are going to show up. Let's come back to that. So that cosine inverse step is where two solutions are going to show up. Let's just proceed with the one that we've found so far, the 1.31, and see where this leads. So before we did cosine, right before that, we multiplied by pi over 183. So we're going to divide by pi over 183. So I'm going to take my 1.31 and divide by, I need parentheses now, pi divided by 183. And that'll give us a 76.44. And then the last thing that happened, or the last thing that we need to do is undo this minus 172. And so we'll just plus 172. And then we end up with our 248. So if we start with 13 and follow these steps, we end up with a 248.44. So that gives us the September 5th. What are we going to, how do we get at this April 6th? Where's the April 6th in all this? Doing this process, that cosine inverse is the step. That's where the two values should show up, because all the other ones are invertible functions. It's this cosine inverse. That's the fishy parts. This is where the two solutions need to show up. Any questions? Comments? Deep thoughts? So what we've noticed is that this process got us to the 248. How are we also going to get the 96? So this process got us to the 248s. What do we need to do to get the 96? That's the big question. Any questions? Comments? Snide remarks? Few reasons I wanted to go over this. First of all, the point is not just solving the equation. If the point was just solving the equation, the instruction would just say, just grab your calculator, grab a graphing calculator, look at the graph, see where it crosses 13. But this is more than just coming up with the days of the year where there are 13 hours of daylight in Grand Rapids. So one of the points that I want to make is that when we have a function, we want to read it as a bunch of operations that we're doing to an input. This is just a list of things that is happening to the inputs. If we want to try to solve the equation, then we just need to undo those things by performing inverse operations in reverse order. If you start with their feet and do plus sock, then plus shoe, you end up with feet and shoes and socks. If you want to get back to bare feet, you have to perform inverse operations in reverse order. So first you take off shoe, then, or you subtract shoe, and then you subtract sock, then you're back at bare feet. You can't do those in a different order. You can't subtract socks first and then subtract shoes. I suppose if your socks had a big hole, you can pull them all the way up over the shoe and then back over the shoe. So, but then you don't really have a sock, you just have a tube of fabric. So it's not the same thing. So don't try to sneak around the problem. You know what I mean? If you start sneaking around the problem, that's just you going, well, actually, and then everybody else in the room rolls their eyes. They might not do it where you can see it, but in their mind, they're rolling their eyes at you. Any questions? Comments? Deep thoughts? All right, next week is when we're going to start tackling this solving of the equations business by using these inverse trig functions. We got to learn how to use these inverse trig functions. Some of you may have noticed already that these functions, these trig functions, are not invertible. They don't pass that horizontal line test. So it's really fishy when I start writing things like cosine inverse. Everybody was cool with it back when we were solving right triangles because it was nice and simple and nothing weird was going to happen. But moving forward, we're going to have to deal with this inverse cosine business. It's not passing this horizontal line test. There's an infinite number of y, or that x, that correspond to the same y. All right. Keep working on your graphs. You got 4 graphs that you have to find equations for. It's in discussion style, so you have to post your answer. Then you'll be able to see everybody else's answer. You might want to practice using the equation editor to post nice, cool looking functions for your graphs. And then while you're, after you get yours and you see what other people chose, try to write a different function for the same graph. If you use positive cosine, try writing one with positive sign or negative cosine. Try to write more. You've got to do one on your own, and then you can get help from everybody else. Any questions? Comments? Deep thoughts? All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.